earlier, but that will be just for us a reference point. All right. Welcome everybody to the seminar of the International Institute of Physics. And our guest today is Dmitri Efetov from Ludwig Maximilians University in Munich. So Dmitri received his PhD from the Columbia University, and after a postdoc at MIT, he joined the Institute for Photonic Sciences in Barcelona. He led the group in low-dimensional quantum materials in ICFO in Barcelona, and this group was working on new quantum effects in low-dimensional materials, novel materials like graphene, and applied these to quantum sensing. So for his research, Dmitri's lab and Dmitri were acknowledged by different agencies and foundations in Spain. In particular, his lab was one of the pioneers in reproducing superconductivity in magic angle twisted bilayer graphene. And currently, Dmitri moved to Munich. He is a chair of solid state physics at LMU. We want to thank Dima for accepting our invitation and for giving this talk today. So before we start, let me just check. Valdelino, are we recording? I think we haven't started recording yet. I just remind we also
recording in progress.
The transmission in YouTube, and if you want to ask a question, so please use the raise hand feature of Zoom, or if you're in a tutorial, raise your hand, or if you're on YouTube, just post your question in the chat, and it will be forwarded to the speaker in the end of the talk. So thank you very much, Dima. Again, I pass the word to you.
Okay. Yeah, thanks very much, Dima, for inviting me to give the seminar. Again, I will talk about magic angle bilayer graphene, and I will give a little bit of introduction on the topic, but also I'll talk about some rather recent results which we worked on in the last year. And basically, okay, so we can switch. Okay, basically this is going to be the outline. So I'll give a little bit of introduction, and then I'll talk about quantum criticality, that we recently observed in the system, which resides close to quantum critical points in the phase diagram of twisted bilayer graphene. I will also talk about magnetic Josephson junctions, which we can create from these materials. And these Josephson junctions are basically monolithical, meaning that we can create them out of all the different phases which are encompassed in twisted bilayer graphene. And last but not least, if time allows, I'll talk also about a new system that is called magic angle trilayer graphene, which is basically the continuation of stacking orders of magic angle graphene. But before I go into details, just let me present my group and also thank the people who worked on it. So again, we're a group at ICFO in Barcelona, and we are currently completely relocating to Munich. So basically in August, we're completely relocated, and all the group members and equipment is going to be there. So Munich, we're also part of Munich Quantum Valley and Munich Quantum Center for Quantum Science and Technology, which is basically a big initiative of Max Planck Institute and universities in the Munich area to foster quantum research. And also I want to thank collaborators, in particular theory collaborators, Andre Bernavik, Leonid Levitov, Ashwin Rithavan, Alan McDonald, and many more. And so really jumping into the topic, so really Moiré materials have excited the field of two-dimensional materials quite heavily in the last 5 years, I would say. So since the discovery in 2018 by Pablo Carrero of superconductivity and correlated state in twisted bilayer graphene, there have been many other phases realized here. In particular, in addition to the superconductivity and correlated insulators, we have also found rich sort of magnetic phases, non-trivial topological phases, alleged strange metal phase, which I will talk more in detail here, and also the superconductivity as the current debate unfolds. While there is no consensus, of course, on the matter, it's believed to be unconventional, and it's been believed to be more closely linked to other unconventional superconductors like pictides or cuprates and heavy fermion systems. So what I also want to immediately mention is that this new platform of twisted bilayer graphene is also special in the sense that it while it shows very similar physics to what has been, for example, observed in other strongly correlated systems, such as in crystals or in optical lattices, there's sort of length scales and energy scales which are defining that system are different. So, for example, in cuprates, we of course have also modulating phases, strange metals, superconductivity, but here the lattice constant in the crystal and sort of the distance between two electrons on the lattice side is only a few angstroms, which then gives rise to rather large interaction energies of electron volts. And in optical lattices, it's of course on the other end of the spectrum. The distances here are in the order of micrometers, and therefore interaction energies are also extremely weak in pico electron volts, and you need to cool these systems down to nanokelvin to even observe anything. And so Moiré materials like magic angle graphene here occupy sort of a sweet spot between the two. They are here, the length scales are in the orders of 10 nanometers, and the interactions energies are therefore in the milli-electron volts. And I also want to mention that not only do we now have this one system, magic angle graphene, but we also have many other systems which can be prepared in this same sort of configuration, such as two-dimensional semiconductors, two-dimensional magnets, two-dimensional superconductors are being prepared by other groups. They're really this sort of new trick of creating these Moiré superlattices and inducing interaction into these. This is really a universal trick, it seems, which some call twistronics, some call Moiré materials. but this is really a more of a universal trick now to manipulate these materials. And to give you some flavor of the richness of this material, and also to give you a little bit of a taste of the sort of measurements and phase diagrams that we obtain. Here is a typical, or like a rather, I'd say it's not typical, but it's one of the nicer devices which were measured with transport in magic angle twisted bilayer graphene. And this really just shows you resistance. Here, one axis is resistance, the other axis is Hall voltage. So basically, this is the Hall resistance in a small magnetic field as a function of carrier density. And carrier density we can control in these systems very easily by applying electrostatic gates. So we can connect a small voltage to the device and capacitively induce electrons into the system. So without changing the device itself, without changing the chemistry of the device, we can just capacitively load in electrons and load electrons out. And we can basically translate this carrier density into electrons per lattice side. So basically electrons on a Moray superlattice. And so, and this is basically the axis on the top here. So filling factor 1, 2, 3 corresponds to 1, 2, 3 electrons per lattice side. And so what you can see here from this graph already is that their resistance changes quite dramatically. So for example, these red regions here in the phase diagram as a function of temperature, these are, for example, insulating regions where resistance goes to extremely high values. And these insulators appear exactly at the integer fillings at -2, 2, 3, and other integer fillings of electrons per lattice side. And these phases we have identified over the last years to be correlated insulator phases, basically phases similar to MOT insulators. Flanking these MOT insulators, you can already see that there are regions where resistance just drops to 0. And in this dome-shaped fashion, flanking some of the correlated insulators. And indeed, identifying these phases in more detail, we can observe superconducting properties of these phases. And really, by now, sort of the idea is that superconducting phases like to sit next to the integer filling positions, basically next to the correlated insulators. And of course, there's a debate whether these phases are interrelated or not. Then if we zoom in a little bit into the center of the phase diagrams at arbitrary fillings, so away from any integer filling factor, we can observe strange metal behavior. Moreover, at a filling factor 1 here, for example, we can observe magnetic signal. So basically, this we can observe when we measure the Hall voltage as a function of magnetic field, whether we sweep the field up or down. We can observe these hysteretic jumps. And what's special about this, this magnetism is now understood to be not spin magnetism, so not ferromagnetism, but it's rather understood as orbital magnetism, which is given rise by symmetry breaking and valley polarization of the bands. And moreover, what you can already see here, what you can guess at least, that this Hall signal at 0 field is close to be quantized to h over e squared. So it's close to one quantum of conductance here. And this is not perfectly quantized because probably the device is disordered, but really it's striking that it is being almost quantized. And this is basically the Chern insulator features, which we also observe more clearly at slightly elevated magnetic field. And those Chern insulators are basically topological states, which sometimes persist down to 0 field, which are then 0 field Chern insulators or topological insulators, as you like. And really to summarize, this is really what I want to emphasize is that this is measurement which was taken on one single device, which is just a homogeneous device that by applying some little capacitance, some little voltage to the backgate, you can tune from one phase to another repeatedly without any degradation of the device. You can study transitions between the phases continuously without changing the device. And also by applying a little bit of a magnetic field, you can also get all these orbital magnets and Chern insulator states. So basically, I think it's a really clean, tunable, and rich platform for these quantum states. And I think we're really excited about these sort of possibilities that this new material platform offers. And to give you a little bit of an idea how actually simple it is to fabricate these materials, that's what, I mean, we just discussed with Dima how much Scotch tape one needs to fabricate these devices. And really, it's really still the best devices we really fabricate still with Scotch tape. So we can exfoliate any single layer material of a van der Waals material that we want. So for example, often this is graphene or HBN that we use for the assembly of these devices. And also we have developed over the years this co-lamination transfer technique, which allows us to assemble these devices one on top of one another. And so what this allows us to do is really to choose any sequence of material species that we like. So we can assemble insulators, metals, superconductors, ferromagnets, Dirac materials, topological insulators, you name it, any material with any sort of, from the library of quantum metaphysics phenomena, you can assemble with one another like that. And not only are these materials really you can assemble it this way, but they also show very nice quality. So basically, if you get now a transmission electron microscopy image and you measure sort of the quality of the interfaces between these layers, you find that these materials have rather clean interfaces, and you find regions which are really perfectly hybridized, perfectly clean interfaces, which then allows us really to observe this rich physics. And of course, one thing I also want to emphasize is that this principle of creating a Moiré superlattice is really relying on this technique, because only with by starting assembly from the platform of 2D materials, we can change the orientation between these materials as we like, and therefore create these Moiré superlattices. And I want to contrast this a little bit with whatever has been done years before van der Waals heterostructure. For years, basically, I think since the 70s, heterostructures of semiconductors or complex oxides was a famous topic. And here people learned over the years in a very complicated manner how to glue layers of different materials repeatedly one on top of another, and also use the same sort of approach to create heterostructures. But here, with these techniques, people start with a single atom. So they had to sprinkle atom by atom on the surfaces. And this had the limitation that all the individual atoms would assemble in the same crystallographic orientation as a pattern material. So creating twists and angles between the crystallographic lattices of the heterostructures was really not so feasible in these growth techniques. And this is really something which is entirely different in van der Waals materials, because we start with preformed two-dimensional lattices. We have this tuning knob and control of the crystallographic orientation. And so really what I think the result is that in the system of twisted bilayer graphene, which is basically just two graphene lattices which are taken together and twisted by a degree of 1.1 degrees, which is the magic angle. we get this entirely amazing system, which is defined by the sort of occurrence of ultra-flat bands close to zero energy. So this is basically a typical single particle band structure of twisted bilayer graphene. As you can see, the electronic dispersion relation is defined by this ultra-flat band of around 10 MeV, close to charge neutrality. These bands are also isolated to the rest of the spectrum by these energy gaps, which are separating it from a higher order dispersion band. And because these bands are so flat, basically kinetic energy is quenched, so electrons effectively stop moving. The dominant energy in the Hamiltonian becomes interaction energy U, and we basically get these strongly correlated, strongly interacting electron systems, which are defining the material. And moreover, another sort of peculiarity here is that if one analyzes now the topological properties of such twisted bilayer graphene which was created, one also finds that the two mini beryllium zones which are arising here, they're decoupled from one another because in K-space they are really far away from each other. And also, if one looks at the winding numbers and helicities in each of the beryllium zones, one finds that these winding numbers are non-zero, but they're 2 and -2. And therefore, basically, theorists have found that these bands are therefore topological in nature. It's impossible to find a one-year function for these orbitals. And therefore, basically, what we have is we have a churn band that are defined. So to summarize, really, we have ultra-flat bands where kinetic energy is quenched, interaction energies are strong, and which in addition are topological. Okay, so moving on then to my first sort of more in detail discussion about quantum criticality and the temperature zero limit, which basically will discuss some of these phases which I have just introduced. So, and I want to really make here directly the sort of analogy, draw sort of a phenomenological analogy of the phase diagram, which we have found in our paper. I will, in the end, I will talk. I will show this phase diagram in more detail. But if you look at this phase diagram, which we have found in magic angle twisted bilayer graphene, and compare it naively, in a very sort of naive way, to the phase diagrams which people found in the cuprates, in condor lattice systems, and iron chalcogenides, in ferroelectric materials like STO, and also in antiferromagnetic materials, they all have in common that there are often superconducting states very close to some sort of ferromagnetic or antiferromagnetic phases. And that also accompanied these phases, they're strange metals. And these strange metals are usually living in a completely different density or phase space regions than, for example, norm or Fermi liquids. And these strange metals are identified as phenomenologically as linear temperature dependencies and magnetic field dependencies at ultra low temperatures. So unlike a Fermi liquid, which usually scales as a power law as a function of temperature, these strange metals scale linearly with T. And also usually one accompanying feature is that the metallic state has a Plancking scattering rate, which means that if you extract the scattering rate of the electrons from the metallic state, you find that it scatters as fast as what is allowed by Heisenberg's uncertainty principle. And therefore, even at ultra low temperatures, these materials scatter like crazy, even without in the absence of any obvious scattering mechanism. So this is why this is what we wanted to identify in our study, and we wanted to really take a closer look at these stage metal phases and compare it to other materials. So before I start with the details, I also want to mention that in principle there were already two works in twisted bilayer graphene, which kind of touched base upon this topic. So there was, of course, the paper by Pablo Carrillo Ferrero early on in the field, which reported some sort of a linear temperature dependence and also Planck scattering rates in graphene close to the magic angle. And basically, they really measured just resistance as a function of temperature. And in an interval of 1 to 30 Kelvin, they observed these nice linear temperature dependent curves. However, there was immediately, after that, there was immediately the group of Andrea Young who kind of picked up on these results, and they really explained that really in graphene, in principle, linear temperature dependencies can exist. And these linear temperature dependencies can actually be just given by phonons. And so in order to really settle the issue here, to really find much more evidence than was given before, we try to really first understand what is the governing principle of electron-phonon interaction in graphene, and also try to create experiments where we can distinguish the two effects from one another. And so to do that, let me just tell you what we know from electron-phonon scattering in graphene. And this is work which I have been working in my PhD. So this was my first PhD paper, actually back in 2010. And I back then investigated just the electron-phonon interaction in single-layer graphene. So no twist, no second graphene layer, no interactions. So this is really just boring single-layer graphene, where the transport properties are completely explained by electron-phonon interactions. And so what in graphene we find is that really indeed we find that linear temperature dependencies exist. So when we analyze our resistance versus temperature curves, they're always at higher temperature some regions where we can draw straight lines through the data. However, at lower temperatures, the data becomes a little bit more power law dependent. And this is better seen if we now subtract the residual resistance and we plot it in a log-log scale. Then one can really see that there is a T to the 4, sort of basically a power law dependence at very low temperatures, which goes up to several tenths of Kelvin. And above these tenths of Kelvin, so at the high temperature regime, like at 100 Kelvin, we really observe a linear temperature dependence. So in this linear temperature dependence, again, this is what we want to distinguish from the strange metal phase. And basically the block mechanism physics here dictates the following. So this electron phonon transport is basically explained by quasi-elastic electron acoustic phonon scattering, which typically is defined by sort of Debye temperature. So basically, in normal metals, you have really large Fermi surfaces, and you have relatively low Debye temperatures, and you basically get into this linear temperature regime only above temperature which is defined by the Debye temperatures. And usually this is hundreds of Kelvin. This is really extremely high temperatures. But in graphene, we have the peculiarity that the Debye temperature is actually not defining the scattering process, but it's a reduced so-called Bloch-Grüneisen temperature, which is a characteristic for this process here. And this Bloch-Grüneisen temperature is directly proportional to the size of the Fermi surface. So because in graphene, we have extremely small Fermi surfaces because it's a semi-metal. Usually Fermi surfaces are much smaller than the size of the brilliant zone. Only a few select quasi-elastic processes between electron phonon scattering are allowed. And this Bloch-Grunhausen's temperature effectively restricts these processes from happening and allows only low energy phonons to partake in that process. And so this Bloch-Grunhausen's temperature is therefore proportional to the size of the Fermi surface, and therefore proportional directly to the carrier concentration that is given in the graphene. And so if one now plugs in sort of this Bloch-Grunhausen temperature in the calculation for resistance, one really finds that there is a T to the 4, T to the 4 component at low temperatures, which then quickly becomes a linear T component if you go to higher temperatures. And so now the question, of course, is how can we translate these findings to twisted bilayer graphene? In twisted bilayer graphene, we have two peculiarities which we have to consider. First of all, we have strong Fermi surface resets close to a density of 2. Basically, when we have a filling factor of 2, we have a Fermi surface reset and carrier density become very small. Therefore, Bloch-Grunhausen temperature also can become very small. And secondly, we have here a very small Fermi surface, Fermi velocity, sorry, in twisted bilayer graphene. So because the Fermi velocity here is in the denominator, also the slope that you observe in this linear temperature dependence can be in principle quite high. And therefore, this could in principle also explain the Plancking scattering rates because the slope of the resistance is so high. The scattering events are particularly strong. And so, in principle, yes, in principle, what Andrea Young's group worked out is feasible. However, one can also find regimes where this is not going to be true. So first of all, this regime would be below 1 Kelvin. So Bloch-Grunhausen temperature, no matter how small it becomes here, would only give you an upper bound until which the linear temperature dependence can persist. So if you would devise experiments which would go well below 1 Kelvin, maybe to 10 millikelvin, to really try to get close as far as possible to absolute zero, photons would be frozen out, and you would have basically a linear temperature regime that would persist down to 0 temperature, which then obviously cannot be explained by phonons. And so this is what we did. So we tried to come up with devices which were having a very broad metallic regime that we could, without phase transitions and without any sort of convoluted other signatures, we could trace back the metallic regime all the way to millikelvin temperatures. And so these devices, this is the devices which we published in some previous work, where we showed that we can effectively screen correlated states in the system by using extremely thin dielectric constant and screening layers which were defined by some graphite gate. And these devices is seen here, and sort of the resistance as a function of carrier density. These devices really have extremely broad and uninterrupted metallic phases. And here we could really cool these devices down to almost 40 millikelvin. And we could really trace this linear temperature dependence over orders of magnitude, over 3 orders of magnitude in temperature, and really try to see what's going on here. And so this is now really the data which we obtained for this device. So the data I'm showing here is on the left-hand side, this is resistance as a function of temperature. So what you can see here is that close to the center of the band, close to the middle of the carrier density, which defines the middle of the band. For example, here filling factor 1.6, filling factor 2, filling factor minus 2.8. The temperature dependence looks very linear, and it continues to be linear almost down to zero temperature, which you can see here. And this is really something which, again, if we replot that data on a log-log scale, and which allows us to see the low temperature regime in a little better way, these curves we can really trace very, very precisely, and we can really convince ourselves that this linear temperature dependence persists all the way to 40 millikelvin, and from those 40 millikelvin, it goes all the way up to around 30 Kelvin. So over 3 orders of magnitude, we have here a linear temperature dependence which penetrates all the way down. And really, what is the most sort of striking point that we want to mention here is that really, if you would estimate the carrier density and the twisted Bloch-Gründers temperature, which we would obtain from the Hall density here, then Bloch-Gründers temperature for all these curves would be way above 1 Kelvin. So in principle, from an Elgin phonon picture, you would only expect the sort of high temperature regime to be linear, but you would not expect the low temperature regime to behave in such a way. So in principle, this is really already a big indication that what we see is really a linear, close to what is believed to be a strange metal phase. But of course, there are other evidences of what a strange metal phase should look like. So for example, also, as I mentioned before, one important ingredient is the magnetoresistance that we can measure in these devices. And this shows basically typical measurements. Resistance is a function of magnetic field, where we also find strikingly a very linear magnetoresistance in this device. And this magnetoresistance becomes, again, especially predominant when in the same temperature ranges that I have just explained, where the strange metal phase lives in the temperature scale. So the magnetic, sort of the occurrence of this linear temperature dependence and this linear magnetoresistance are basically happening at just the exact same temperature ranges that I have just described. And they disappear in other temperature ranges. Furthermore, I also, of course, what we were able to do is to extract the scattering rates from these measurements. We just used Drude equations, where basically by measuring resistance, density, and the effective mass, you can extract tau. And the effective mass we extracted separately in separate measurements by analyzing the temperature dependence of the Shubikov-de-Haas oscillator. And really what is striking for basically, if you plot tau as a function of temperature for all these curves, which I just showed you, really the strange metal phases, so basically whenever we have linear temperature dependence, we also have blanking scattering rates for these metallic phases. And again, the temperature ranges are coinciding perfectly with that. And so basically, basically, I think what's really striking is that really at even at 40 millikelvin, where in principle almost no phonons are populated anymore, where everything's supposed to be frozen out, where impurity levels we know are not sufficient for this type of scattering events, we end up having such as extremely fast scattering rate. And of course, the question is what can do the trick? And I will come back in a second to this. So just another control experiment that what we did is, of course, as I mentioned, we believe that all these physics is tied to the magic angle condition. So of course, what we can do in our experiments, we can just tune the twist angle slightly away from magic angle. So we know that if you tune the device twist angle to 1.4 degrees, this is very close to magic angle, but there the interactions, the flat bands and the interactions disappear, and 1.4 degree device behaves more or less like single layer graphene should behave. So no interactions, no sort of quantum phases that we observe here. And indeed, so we tested a number of devices which are away from twist angle, from magic twist angle, and we don't see the strange metal phase. So if you look at the temperature dependencies of these curves, they all look like power law behavior with a linear temperature dependence at high temperatures. So really, it looks like single layer graphene, and is really, we can strongly distinguish these phases from what we observe at magic. And so one thing which is also interesting, of course, as I mentioned, so we also observed a superconducting phase in this phase diagram. So of course, we like to see whether the strange metal phase and the superconducting phase are kind of also overlapping. And for this, what we could do is we could just measure sort of the typical resistance as a function of temperature in the superconducting state. So we would get this transition temperature of around 500 millikelvin here, where the resistance basically drops to 0. And we would be able to apply a perpendicular magnetic field to kill the superconductor and to really look at the metal which is left when the superconductor is gone. And really, we did this, and we find that even when the superconductor is gone at 300 millitesla, the linear temperature dependence persists. Same happens for the magnetoresistance. And of course, basically, this allows us to kind of ask the question whether what about the parent state of the superconductor. So in principle, by all means, the superconducting phase is born out of a strange metal phase. So whether these mechanisms for the one or the other are related, this is a completely separate question. But at least the superconductor and the strange metal phase, they are coinciding here. And so with this, really, I think the field is, this field is open up for interpretation now. Of course, in the past, many people have over the years studied strange metal phases. This is by no means any sort of by no means this is any complete library of things, but there's been many countless people working on this. But one sort of popular assumption is that really these strange metal phases appear close to sort of magnetic phase transitions, where, for example, from a fermiliquid to a magnetically ordered phase, and close to a quantum critical point, which is sort of defining this phase transition, magnetic fluctuations can give rise to this extremely fast scattering mechanism. And of course, in twisted bilayer, we know, as I mentioned before, we have a multitude of magnetic phase transitions. We know from previous work, for example, by the Pomeranchuk effect, that such magnetically ordered phases are present in the system. So of course, this naturally raises the question whether these two effects are somehow related, or whether these magnetic phase transition can give rise to such physics. This is, of course, an open question, but I think for fun we can try to make such analogies. And really, last thing I want to say here is really to summarize. So the phase diagram which we obtained here is really the following. We really, if you look at the sort of the phase diagram as a function of temperature and density in one of the flat band regions that we have, what is striking is that we really observe Fermi liquid behavior very close to the band edges, here to the insulator band edge and to close to charge neutrality. So those Fermi liquid states are basically just described by a power law, T to the squared, in the resistance. And those states are understood as Fermi liquids where basically close to the band, where the density of the metal becomes really, really low, interactions become a little bit weaker, or the Fermi liquid basically establishes itself. But in the center of the band, where interactions are the strongest, we really develop this broad strange metal phase, which is probably given by the phase transitions which we typically observe with the integer fillings here. And this strange metal phase encompasses, for example, this superconducting dome region, which is really where the two phases basically coexist. And so, again, this is, I think, would be fun to think about what it all means. As far as I understand, strange metal is not really understood, not explained. So I don't think there is a consensus of what exactly is making these metals strange. But I think we present here compelling evidence that at least phenomenologically, whatever we observe here in twisted bilayer graphene is similar to these other systems like cuprates, like peptides, like heavy fermion systems, and so on, that show very similar phenomenological behavior. And the rest is up for interpretation by theorists. Okay, and then last but not least, so I think I have maybe still 10 more minutes. I want to just go quickly through some work that we've done on magnetic Josephson junctions. This is a little bit of a shift of gears I will make here. And really, I want to just briefly glimpse through my introduction that I gave you in the beginning. So as I explained in the beginning that in principle, there are topological Chern bands that are defining the band structure of twisted bilayer graphene. And these Chern bands in principle can be polarized by interactions. So basically, if we break C2T symmetry of these bands, we can open gaps between them, which give rise to topological features, but also these gaps can, for example, happen in one valley versus the other. We get valley polarized states in graphene. Exactly, without going into much of a detail here, we have observed such states at elevated magnetic fields, but in particular, as I mentioned before, we have observed such states, for example, at zero magnetic field at a filling factor 1, where we really observed in the whole signal as a function of the direction of magnetic field that there are these magnetic hysteresis loop forming, and we can attribute these states to orbital magnetic states, which are almost topologically quantizing the RXY signal. So, so this type of magnetic states are, we thought it's very interesting to hybridize, for example, with magnetic states, with superconducting states. And I mentioned to you in the beginning that really these magnetic states, which are showed here, they reside basically at one filling factor, at one electron per unit cell. However, if you just change the density a little bit and you move in that direction, you find a superconducting state. So in principle, just by electrostatically changing the voltage on your gate, you can induce transitions between superconductivity and magnetism. And so we really liked to create devices that hybridize these states with one another. And so, right, and so these are sort of the devices which we made. So these devices consist of top gates graphite and a graphite backgate, whereas in the center you see the magic and graphene. And what we can do is we can now locally change the density in these devices, and we can basically create devices which are where the density in a local region of around 130 nanometers, which is defined by the slit, is different from the density everywhere else in the device. So what effectively this geometry allows us to do is to create junctions where the leads of the device are tuned into the superconducting state and are kept superconducting, but the center region of the device is tuned into any other state, which is basically in this phase diagram. And also it can be tuned, for example, in this filling factor 1 state, which is magnetic. So in principle, this geometry allows us really by electrostatic tuning, to create homojunctions. So basically, again, without any chemical doping, but really just by electrostatic gating between superconducting phases and the magnetic phases, but also any other phases that we observe in the system. And so without going into detail, so we create double gated maps like that. And by investigating these gaps in more detail, we can really clearly define regions where along which we keep the superconductors fixed, and we really manipulate only the inner region of the of the device. And so this is how the sort of maps look like that we investigate. So the color map here shows DVDI measurements as a function of NJ and as a function of critical of current. And NJ is really the density in the central region. So again, the leads are just superconducting. We change only the density in the central region, and we can do it continuously, sweeping throughout the different phases for the central region. For example, a normal metal region, a superconducting region, and a correlated insulator region at -2. And what we find is that really the different junctions that we form in the process have very peculiar properties. So for example, if we zoom in into a junction which was created at this density, this is really a proper SSS junction, so meaning that it's no junction at all if you want. This is really just one big homogeneous superconducting state. And as you can see, so if we measure DVDI as a function of current and magnetic field, we just find sort of the critical field and critical current, which is basically identified by these diamond shape, but we don't find any signature of any Josephson junction in the system. However, if we tune away now the central region to a normal state, so we form a SNS junction, we quickly start to see Fraunhofer interference patterns. So this is really a tell sign that what we are doing is inducing a Josephson junction and basically separating the superconductor in the middle. But moreover, if we now tune the Josephson junction with the central region in the correlated insulator state, we can find a really strong superconducting Fraunhofer interference pattern, which is also very peculiar because, as you can see, it is somehow tilted. It's asymmetric with respect to the critical current and magnetic field directions. And basically, if we zoom in on this Josephson junction, we can really see how strange it is. So first of all, if we take line cuts here at, for example, magnetic field, at a fixed current as a function of magnetic field, then we can see sort of in the DVDI versus field signal that there is really strong dependence on the field direction of magnetic field. So again, sweeping up, we get a certain Fraunhofer interference pattern. Sweeping down, we see that the Fraunhofer interference pattern switched, so it's anti-symmetrized somehow, and it also phase shifted. Same thing we observe for DVDI as a function of current, whether when we premagnetize the sample to positive 30 millitesla or negative millitesla, we can find that its polarity somehow changes and really switches switches in the process. So how can we now understand this? So first, as I mentioned, so we immediately looking at such signatures, we immediately start to believe that there is some magnetic switching happening in the junction. And of course, we wanted to quantify this a little bit more. So we have, for example, measured the system when applying a per minus 300 millitesla field. As you can see, so the junction is tilted to one direction. When we apply a negative, a positive magnetic field, the junction is tilted in the other direction. But whenever we warm up the system and we cool it back down, the DVDI characteristics are again completely normal and completely symmetric. So something really magnetizes the system, and really before we ever apply for the first time a magnetic field, this magnetization is gone and it really disappears by warming up and by cooling down. And the other thing is, of course, we took these hysteresis maps. So basically, we took the Fraunhofer sweeping only in the up direction and the Fraunhofer sweeping only in the down direction. You can really clearly see between the two color plots here that there is a phase jump between the two curves. And really, by taking now line cuts and comparing them as a function of sweeping up and down, we can really see that there is a clear phase shift developing below 800 millikelvin, which is getting stronger with temperature. So from this phase shift, we can identify a critical temperature to the device, to this magnetic phase, which is around 800 millikelvin. And really, this critical temperature is very different from the TC of the superconductor. So TC of the superconductor is around 3 Kelvin, and really the Josephson junction above, below just 3 Kelvin does not show this hysteretic behavior. This only develops below 800 millikelvin, and therefore we think it's basically a sort of magnetic phase with a Néel temperature of 800 millikelvin, which develops in the process. And so one question, of course, we wanted to know is what type of magnetic state could produce such results. And for this, without basically excluding any other state, but one possible candidate state in the process here would be a valley polarized state, where basically one valley is occupying two Chern bands, giving you a total Chern number of -2. And the other valley is unoccupied, completely unoccupied. So what one can do with such a valley polarized state, one can basically just calculate the Berry curvature winding numbers, and one can also calculate sort of the loop currents which are created in the states. And we find that there is an orbital magnetization of the state which is given by around 10 bar magnetron. So we can quantify the size, the magnitude of this magnetic state. And another thing which is really which we really found in the past, and other sort of people who worked on these marine systems, is that this magnetic states, they're often can be switched by currents. So basically, depending on the applied current direction, you can switch the magnetization of the state up or down. So basically, the current couples to the magnetic moment of this, and it can really reverse and switch it. And so those are also things which you don't expect from a ferromagnet to be happening. And so we, of course, try to see whether our experiments fulfill those signatures. So first of all, we realize that we have a phase shift of Fraunhofer. So if we look at the 0th order current peak in our Fraunhofer, it's phase shifted from 0 but around 3 millitesla, which corresponds to around 3 to 4 Bohr magnetron. So this is, again, much bigger than what you expect from a spin ferromagnet, but it's relatively close. It's consistent to this orbital magnetic state that we propose. And the other thing is, which is even more striking, is the sort of current switching of the Fraunhofer. So really, depending on the sweeping directions of the current, we can have a phase shift, which is induced just by the sweeping direction of the current. And this is, again, in line with what was previously observed for these orbital magnets. And last but not least, this asymmetry of the Fraunhofer has also some practical implications. So, for example, we were able to show that critical current in one direction can flow, whereas at the same critical current in the other direction, no superconductivity is observed. So this is really identified by these density by these windows in current, which you can see here, where really we can switch by applying a certain current direction. We can show that it is superconducting in one direction and resistive in the other direction. And of course, we can also program this diode effect by applying a magnetic field and by reversing this diode behavior. Okay, and with this, I'm actually, I think I'm done. So I think I'll stop here. And I again, thanks very much for your attention and the invitation to give the seminar.
Okay, thank you very much, Timo, for this great presentation about these fantastic materials. And let us pass to the questions. If you have any questions, I will open the chat if you want, or just raise your hand to ask the questions. Yeah, so we have one question here in the auditorium.
So thanks for a nice talk. I have two questions. You showed a plot of the resistivity, the dependence with the twist angle, and there are two regimes, one where you see Planckian transport and the other can be explained by the usual phonon interactions in graphene. How fine-tuned this twist angle must be to actually observe Planckian transports? It's like very fine-tuned. There's a
it's So basically, right. So basically, you see. So those are the devices which show linear temperature dependence of Planckian transport. Those are 1.10, 1.14, 1.03, 1.02. And even 1.3 shows it, but slightly. And then at 1.4 and 1.5 degrees, this effect is gone. Then you get a t-squared dependence.
Oh, right.
So it's basically 1.1 degrees plus minus 0.2, I would say. That's where you can see it.
Okay. The second question I have, you showed a correlating insulator in the filling fraction phase diagram. There is some understand why what is it is a fractional Chern insulator? What's the physics there?
Yeah. So okay. So you mean like these guys? Like I think this is close to a fractional filling here. Yeah. So there is there have been several reports now by I think the group of Andrea Young, etc., and some maybe Eva Andre had something, right? That really see these states, these resistance states, and these correlated insulating peaks appearing at fractional fillings. Like, for example, I think this was 3.5, so it's 7.5, so something like that. Those are, I think, usually interpreted as charge density waves. Whereas I have to say that in another platform, in TMD materials, this is work done by Kin-Fai Mack, for example, they somehow observed many more of these fractional phases. So they observe almost any fraction that you can think of, really a rich sequence of fractional states. And they interpret them as Wigner crystals, charge density waves, you name it. So whatever sort of arrangement of on a lattice you can think of, but even Wigner crystals, they seem to observe.
Oh, I
In
see.
twisted bilayer, we don't see it that well actually. So these optical systems, they're more sensitive to it somehow.
Okay, thanks very much.
Okay, thank you, Raphael. I have a question, or maybe a couple of questions. So, first about superconductivity in twisted bilayer graphene. I think the early question when this effect was just observed was whether this is what type of superconductivity it is, and I know if this has been settled already. So, if you can comment on that.
Yeah, so it's I would say that there's absolutely no consensus, so it's not been settled. Um, um, I have to say that when the field just began, it was very strongly, there was a very strong opinion. It's like the cuprates. I think then we went to a phase where things were in doubt, and a lot of people were proposing electron node scattering mechanism. I think these days, if you go to any conference, probably 80 to 90% of the people think it's very unconventional, it's very unusual. But it's definitely different. Probably the differences to cuprates are quite striking still. But I think still a lot of people would think that it has something to do with the symmetry breaking, this sort of these sort of magnetic phase transitions that we observe here. But I think you know, there are as many theories out there right now than and opinions. But most of them really, I have to say, most of them would probably tell you some unconventional origin.
Not BCS like.
Maybe exactly. Maybe it's a self-sustained thing. Maybe people like to think it's more exotic than it is. I don't know. But we in this field, as I mentioned, we went through phases and now I think we're now in a stable phase where we agree to disagree, but we all think it's maybe not so trivial as one might think.
Yeah, I think you actually answered my another question is relation to cuprates. So it is, I think, as far as I understood, that well, the status is actually unclear, but it looks like it's not exactly cuprates. So my question
It's definitely not.
My question was whether you can think of twisted bilayer graphene as some kind of more clean system where you're under more control, where you can understand the cuprate kind of behavior.
So I would be careful with that, because I think for sure what I can definitely say is there are things that we really can do with graphene that people would only dream of doing with cuprates. And this is, for example, these screened interactions, which is this slide here. The screening here by external gates, etc. This is something you cannot do in a crystal system at all. This is not a parameter which you can change there without chemically overdope the system and completely change also the disorder profiles, etc. So, and of course, all this tunability, all this these transitions that we can map out in a clean way, that's an advantage you have here for sure. But I have to also say, of course, there are also things that we cannot do with graphene that people are used to be doing in crystals. So, for example, in crystals, one of the major techniques is, for example, heat capacity measurements, thermal conductivity measurements. People measure magnetic penetration depths. People can extract easily the supercurrent density. All these things in these two-dimensional materials are extremely hard to do, almost impossible to do. Neutron scattering we cannot do to study the antiferromagnetic phase in more detail, for example. So I would say that, yeah. So I would say it's really a different material with different physics. we can study it in a different way. So maybe I would, I would really, I think I personally stopped comparing it all the time to cuprates. I think it's interesting by itself. I mean, that's my personal opinion. And whether all of these materials, again, it's not just the cuprates, but also heavy fermion systems, pnictides, etc., whether they in the end share some of the same physics, that's, I think, still generally an open question, right? So I think maybe yes, maybe no, but I think right. I think we will see, I guess,
Okay, we have a
or we
couple.
won't see. Maybe it will take another 30 years of confusion in that field. So I don't know.
We have some more questions. So the first one is from Lauro. Lauro, please, if you can unmute yourself and ask the question.
Hello, Dmitri. Thank you very much for your talk. I'm Lauro. I'm from the University of São Paulo. I'm doing my master degree here, and I'm very interested in studying the magnetic fluctuations in magic angular twist Bilayer graphene. So my question is, what is still lacking in literature about this topic, about magnetic fluctuations in TBD?
So in terms of experiment, there was nothing. There's nothing really. We know. I think in terms of experiment, I can give you. Oh, sorry. I'm sorry. In terms of experiment, those papers here. It's by Shahal Ilani, Andrea Young, and by Goldhaber Gordon. So they observe, for example, the Pomeranchuk effect. So they observe actually a stiffening of these ferromagnetic phases at elevated temperatures. So actually, the funny thing is, those phases at base temperature, at like millikelvin temperatures, are less strong than at 10 Kelvin. So you warm up the system, and the ordering becomes stronger. So this is probably so they performed some thermodynamic measurements of the states, and they find that there's really some signatures of these magnetically ordered phases. Then the other thing is, I mean, we had one study here with, which I haven't shown in detail, with Eli Zeldov, where we were able to map out these magnetic phases. And Eli has worked out that those are really those mosaics of Chern numbers which are forming there. So this is also, even if the device is clean, the magnetic domain structure is very chaotic. And so they found also that strong interplay between the different domain wall regions. In terms of theory, I'm sure you can find them hundreds of papers on this, but I'm not too familiar myself.
Okay, thank you.
Okay, thank you for the question, Lauro. And so the last question, so it is from YouTube, and it's a good question to finish the talk. It is about everyday use of these technologies you mentioned, for example, the superconducting diode. How far do you think this kind of twistronic technologies are from real life? So I'm not sure if I'm offline or Timo went offline. Here, okay. I think the speaker went offline. All right. So yeah, I guess if we're not able to recover him in a moment, then I'll write to. I'd like to thank everybody for participating today, and we'll have more.
Dima, I think he's there.
Yes, Misha.
I think he's there in the list of participants as a co-host. I can see him still.
Yeah, we can see, but we cannot hear him. Well, anyway, so as I said, I thank you everybody for participating. Unfortunately, we couldn't hear the answer to this, maybe one of the most interesting questions of today. But yeah, so I think time will show. But next week we'll have more seminars. So I hope to see you again next week. Thank you very much.